Hi everyone, welcome to CS 188, Section 6, and today the worksheet will cover feature-based Q-learning and probability. So this should be a 6, and that is not correct. Okay, so first we're going to do Pac-Man with feature-based Q-learning. So the problem states that we would like to use a Q-learning agent for Pac-Man, but the state size for a large grid is too massive to hold in memory. To solve this, we will switch to feature-based representation of Pac-Man's state. So say our two minimal features are the number of ghosts within one step of Pac-Man, big FG, and the number of food pellets within one step of Pac-Man, FP. You'll notice that these features depend only on the state, not the actions that you take. Keep in mind as you answer the next couple of questions, so that'll be important. For this Pac-Man board, they want us to calculate the two features. So first, we calculate FG, which is the number of ghosts within one step of Pac-Man, and that's 2. And the number of pellets, FP, within one step of Pac-Man is 1. So that's what our features calculate. So number 2, with Q-learning, we train off of a few episodes so our weights begin to take on values. Right now, WG equals 100 and WP equals -10. Calculate the Q value for the state above. So our equation for the Q value is Q of S comma A equals WG times FG plus WP times FP. So that equals 100 times 2 plus -10 times 1. So that equals 190. Okay. Part 3. We receive an episode, so now we need to update our values. An episode consists of a start state S, an action A, an end state S prime, and a reward R. The start state of the episode is the state above, where you already calculated the feature values and the expected Q value. The next state has feature values FG equals 0 and FP equals 2, and the reward is 50. Assuming a discount of 0.5, calculate the new estimate of the Q value for S based on this episode. So what they want us to calculate is our new sample. So if we remember, our new sample is our reward, S comma A comma S prime, plus gamma times the max over actions of the future Q values. So we can start filling this in. So they tell us the reward is 50, gamma is 1/2, and now we need to calculate this max value. So what do they tell us? So they tell us that the next state has features FG equals 0 and FP equals 2. So we know the features, and if we know the features, we go back up to the problem statement and we notice this. The features depend only on the state, not on the actions you take. So when we want to calculate Q of S prime comma A prime, and we're maxing over A, it actually doesn't matter. So because this A right here, A prime, is never used. Therefore, we actually know the max Q value, and it's going to be the weight G, which is 100, times FG at the new state, which is 0, plus the weight WP times whatever FP is, which right here is 2, and this will give us 40. So note here that the Q value only depended on the state, because the features only depended on the state, but in general it could depend on the actions. This just happened in this specific example. So now question 4, with this new estimate and a learning rate of alpha is 0.5, update the weights for each feature. So using the formula, we have WG equals WG plus alpha sample minus the previous Q value times FG of the current state. So when we calculate this out, this is going to be, the current weight is 100 plus 1/2 times the sample is 40 minus the Q value, which is 190, times the feature, which is 2, and this equals -50. Now let's do the update for the pellet. WP equals WP plus alpha sample minus Q of S comma A times FP of S comma A. Note that the feature is from the current state, not this future state that we calculated in this max, it's the current one. So if we plug this in, our current value of WP is -10 plus alpha is 1/2 times the sample 40 minus the current Q value 190 times the feature, which is 1, equals -85. So what do we notice here? Well, we notice that the weight on the ghost went from 100 to -50, which makes sense because ghosts should actually be avoided. Now, for the pellet, it went from -10 to -85, but the difference is a lot lower than it was before. So it's making progress. And if we ran this more, then the weights would converge to better values. Okay, so now on to probability. So they want us to use this table to calculate the following values. So we're going to use the rules of probability, like I showed in the section video, to solve these. So for A, the probability x1 equals 1 and x2 equals 0, let's rewrite this using marginalization. So it's the sum over all values x3 can take of the probability x1 equals 1, comma, x2 equals 0, comma, x3 equals little x3. So if we look in the table, we have x1 equals 0, or x1 equals 1, x2 equals 0, and there's one instance where x3 is 0, so it's 0.1, plus what happens if we have 1, 0, 1, that's 0.05, so this equals 0.15. Now what's the probability x3 equals 0? So this equals the sum over x1, comma x2, probability of x1 equals x1, comma x2 equals little x2, comma x3 equals 0. So if we sum all the entries that have x3 equals 0, 0.05, 0.1, 0.4, 0.1, this will give us 0.65. Okay, now let's look at C. So C, we now have a conditional probability. So let's rewrite this using Bayes' rule. So we know this equals the probability of the joint, x2 equals 1, comma x3 equals 1, over the probability of x3 equals 1. So if we calculate this out, let's sum up. The top can be rewritten as a marginalization, but I'll just talk this through. So for x2 equals 1 and x3 equals 1, find all those entries. So it's these two right here. So it's going to be 0 plus 0.2, which is 0.2. Now what's the probability x3 equals 1? Well, we can use a little trick. It equals probability 1 minus x3 equals 0, which we calculated in part B. So this equals 0.2 over 0.35. Okay, so now let's look at D. For D, we're going to do the same exact Bayes rule. So the probability of x1 equals 0, comma, x2 equals 1, comma, x3 equals 1, over the everything behind the bar, x2 equals 1, comma, x3 equals 1. Now if we look at the top, 0, 1, 1 corresponds to 0.2. And the bottom is anywhere both x2 and x3 are 1 and 1, and we sum them up. So that'll be 0 plus 0.2. So 0.2, so that equals 1. Okay, now for E, we again use Bayes' rule. Probability of x1 equals 0, comma, x2 equals 1, comma, x3 equals 1. This is divided by probability of x3 equals 1. So if we look up in the table 0, 1, 1, we get 0.2. And we've already calculated a probability of x3 equals 1, and that equals 0.35.